Hi there, this is Fleep, and today I've got a little tutorial for you. Just kidding, this is Ismael. I want to thank Rake for having me here on Guided Hacking. In today's video, we're going to be taking a look at buffer overflows. So before we get started, we're going to write a program that's susceptible to a buffer overflow. So I'm here in my lab environment. I have code blocks just because Visual Studio likes to inline string copy for some reason, and we don't want it inlined. So we're going to do ampersand. No, it's not an ampersand. It's an octothorpe. Octothorpe include string.h int main parentheses your curly brackets return 0. This is hopefully not new to you. At first, well, to start it off, we're going to declare a variable. We're going to call it leet, and we're going to set it equal to hex 1337. Next, we're going to declare a character string array. So we're going to do car, and we're going to name it buffer, and we're going to give it a size of 16. No. Yeah, we'll give it 16. 16 characters, that sounds good. Okay. Now we need to pass in our arguments to main so we can give the program command line arguments. So it's going to be int argc, comma, car, or care. No, it's car. It's something. So argv, and then we're going to call our string copy, which I have the function definition open for you guys. It takes a destination, which is going to be our buffer, and a source. Our source is going to be a command line argument. So let's go back. We said that this was going to be buffer, and it's going to be argv, and it's going to be 1. All right, so let's go ahead and build this. And it looks like it compiled successfully. Let's go in and find it somewhere. It's going to be C projects, bof example, bin, release, and here it is. We're going to open it up in OllyDbg. So this is all that C runtime stuff. So let's just go to search for all intermodular calls, and we're going to look for that string copy. Okay, and we're here. So this is our main function. So I'm gonna put a breakpoint here. Let me go into debug, click on arguments, and at first we're gonna give it 1, 2, 3, 4, 5 A's. Hit OK. It's gonna complain that we need to reload the program, so we're gonna hit OK. Press this little arrow right here, and we can go ahead and press start, and we're at the main function with our breakpoint. Great. So let's go ahead and step over. So push EBP, move EBP, ESP. That's a function epilogue. What it's doing is it's setting up our stack frame, and it's saving the caller's stack frame. If that doesn't make sense, hopefully it'll make sense in a little bit. Just bear with me. Okay, now we see an AND ESP with this string. All that's doing is aligning the stack. Don't ask me why. The GCC compiler likes doing that. Sub ESP20. So that's gonna be for our local variables, that BOF buffer and our leet. But if you notice, we don't see any hex 1337 anywhere. That's because code blocks noticed, hey, dumbass, you're not using this variable. Why am I gonna put it in the code and make it bigger than it needs to be? So it removed it. Whatever. So there's a random call. I'm not sure what that does, but it's not important. Step over. EBP plus C. That is gonna be, what is that gonna be? Our second argument, which is gonna be that's our argument, the A's, I believe. Yeah, it's the pointer to the pointer. So it loaded that into EAX, which is going to be an array, so then it needs to access that second string. Step over and you're going to see the A's pop up in EAX. And there you have it. So now it's saying move EAX into ESP plus 4. So ESP is pointing to the top of the stack. It's going to override this. But I believe it's just going to pass in the address to it. Yes. And now it's going to pass in the destination, which is our BOF buffer. So yeah, like ESP plus 10. Scroll down. Scroll down. And when we call it, we're going to notice the stack. We're going to see 41s appear. 5 of them. There you go. Did you see that? 41, 41, 41, 41, and 41 right here. And then it's clearing EAX and it's returning. So now you might be wondering, why did I show you this simple program? So most programs follow a calling convention. A calling convention is necessary so the operating system can set up your stack frame for you, or so the compiler can set up the stack frames. When I called string copy, how did that program know not to fuck with my registers? It's because of these calling conventions, which I should have somewhere here. So this is a few of them. cdecl. Who cleans the stack? The caller cleans the stack. So if we go back into our program, we're going to notice, we're not going to notice because it's a simple program. It's just clearing it at the end. But normally, when you push arguments to another function, right after that, you're going to see an add ESP, whatever you added onto the stack. So say if I passed in 2 integer values, 2 D words, you're going to see add ESP 8 to clear those variables off the stack. Yeah, I hope that made sense. Alright, so now we need to talk about the stack itself. If we scroll all the way down here, these are the highest addresses. If you notice, these are all going lower. If we scroll up, these are all going lower. The stack grows backwards for some weird reason. So when we're following that cdecl convention, you're always going to see push EBP. What that's doing is that is specifically saving the caller's stack frame. So you're going to see it, like you're going to see this grow by 1, and EBP is pointing to this value right now. And we see that same value on the stack. Now ESP points to the top of the stack, which is here. That 58, we're going to see that same 58 here. We're going to move that into EBP here. And that's how we're going to access our arguments. So step over that, and we see that they have the same value now. Now our stack frame is set. This, like I said, it's to align the stack for some reason. And then we're going to see a sub ESP and then some space for our local variables. And we had said that we wanted 16, which would be hex A, and then that integer leet, but it didn't even compile that into the code, so it's not even important. And you're like, okay, so if you allocated 16 bytes, why is there, what is that? 32 bytes allocated. I don't know. The compiler likes to allocate extra room, maybe to try to protect you from buffer overflows. Who knows? That random call, don't know what it does, not important. So then we know that that second argument that we passed to main is a pointer to a pointer. So we're loading that first address into EAX. We're getting the second. Okay, so now we have an address. We're getting that address plus 4, which is that. Okay, hold on. Getting ahead of myself. Okay. So this would be that first argument, which would be EBP. No, it would be EBP plus 8. And we have EBP plus C, That's this guy here. So now it needs to actually dereference that pointer to get our character string. Ooh. All right. Feel like, okay, doing all right. There's a lot to cover. Okay. So now let's look at a simplified version that I wrote in assembly myself. Here's the code. It's going to be a lot of what I just explained. Here's your function prologue. And then we're allocating just enough room. It's going to be, did I allocate too much room? This is 16. No, so that 10 is 16 plus 4, that's 20 bytes. So it's going to be 16 bytes for our character string, 4 bytes for our 1337. Alright, so now that I subtracted ESP by 20 bytes, it's going to be pointing to the top of the stack. I'm going to set what the top of the stack is pointing to equal to hex 1337. Then I'm going to load ESP plus 4 into EAX. So basically I'm going to get the address before this 1337, so I don't overwrite this 1337. Then I'm going to push a string, because since this is written in assembly, we can't pass in command line arguments because that C runtime isn't there to actually capture that command line argument. So I set it equal to 5 A's, 5 B's, and 5 C's. Alright, so now I'm going to push EAX, which is pointing to our buffer. So I pushed our source, which is our argument. Then I pushed EAX, which is our BOF buffer. I'm calling string copy. And then I'm removing those 2 addresses that I pushed onto the stack. I don't need to do that because I'm going to clear the stack anyways here. But like I said, it's normally done like that. So this is restoring this is removing all our variables from the stack when we subbed ESP up here. This is restoring the caller's stack frame, but there's no caller in this, I guess, case. And then this is needed because I need to call that so it doesn't crash. Alright. Now, let me open this in OllyDbg so you can see it. So we're going to push EBP. We're going to see it, an address pop up on the top of the stack. Boom. Now we're going to set EBP equal to ESP. ESP is currently pointing. ESP always points to the top of the stack. So EBP is going to be set to this value. And we see it there. Okay, now we're going to make some room for our local variables. So we're going to subtract ESP by 14 hex, which is 20 bytes. So you're going to see 5 new addresses pop up here. Let's count it. So this was where we started. This is pushing EBP, and then here's 1, 2, 3, 4, and 5. That's the 20 bytes. Next, what are we doing? We moved 1337 to what ESP was pointing to, and ESP was pointing, like I said, it's always pointing to the top of the stack, and we can see that there. Now it's set to 1337. What we want to do now is, since ESP grows while the stack grows backwards, so if we add 4 to ESP, it'll point here, and that's what we're doing. We're going to do ESP plus 4, load that into EAX. So we're setting EAX equal to 12FFB0. 12FFB0. Now, we're pushing our argument onto the stack. We're pushing EAX, which is our buffer, which again points here onto the stack. Okay, now we're going to call string copy. And look what happens. You're going to see our argument, hex A is 41, 42, and 43. And you see those values right under 1337 going backwards. Everything right now is fine and dandy. We still can see our return to the function that called this function. Okay, so add ESP, we're clearing those two arguments off of the stack. So we're going to see these A's disappear. Boom. Now our 1337 is on the top of the stack again. And then that's pretty much it for our program. We're going to remove all our local variables, which is going to remove the 5 lines. So it's going to remove this, 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 and this. And this again was that push EBP. So let's execute that command. And like I said, this is the push EBP. Now we're going to pop EBP to restore the calling function's stack frame. And then that's it. We exit this program. So now what would happen if first I terminate the program, and instead of abiding by that allocated space, oh shit, what happened? We add a whole bunch more A's and we compile it, or we build it. Undefined symbol. What happened? There we go. I don't know how that happened. Don't ask. What is going on? Shift. I'm pressing Control. That's why, my bad. So now build it, and it got built successfully. So let's load it back up into OllyDbg, and now we can see it's a lot bigger than those 16 bytes that we allocated. So let's see what happens. We push EBP, we see it there. We're setting EBP equal to ESP, so we're setting it to the value that's pointing to the top of the stack. We're allocating some space for local variables. We're setting the top of the stack equal to 1337, which was that integer. And now we're getting the address right below our integer, loading it into EAX, and now we're pushing our argument to string copy. We're pushing that buffer that we just loaded right under 1337 to string copy, and we're calling string copy. Now we know that the stack grows backwards, and we saw it going down. So the last time we ran this, we saw it stop somewhere around here, because we need this return address to go back to the calling function. What's going to happen after I execute it? Well, if you notice, that return address is gone. Everything's been completely overridden by 41s. So we're going to add ESP. We're going to add 8 to ESP, which is going to clear these two arguments that we passed to string copy off of the stack. And then this is going to clear everything up until that push EBP. See what happens. And then this would be that EBP we pushed on. So we're going to pop that. And now, if there was a calling function, when we tried to execute it, it would set EIP, which always points to the next instruction to be executed. If you look at here. If this was an actual program, EIP would be pointing to 41, 41, 41. Can you guess why that is bad? if you're an attacker, or if an attacker I guess exploits this vulnerability, they can control the program. And we're going to see in a little bit why that's dangerous. I just wanted to show you how it kind of works under the hood with a simple example.